we have pretty much anything that we want to do. Hello there, Demonari here, back into a new project. This is going to be a longer project than my previous ones because I'm creating a mini tutorial about making your own game engine. So let's start. Creating a new project. You have your the solution and your project file. I'm using Visual Studio, and the libraries I'm going to use is Glue, the OpenGL extension Wrangler, and SDL2, the simple direct media library. So to do that, I would need to set up my properties. For output directory, I will change all configurations to be set up like this. Solution platform configuration project name. This way every project gets their own folder. This is very important when you're making larger projects that have resources and other files that you want to deal with. You can just do it for release. It is usually better to do it only for release, but for the sake of having a coherent setup, doing it in this manner can actually give you some more tools for debugging problems. You wouldn't have missing resources when you open the debug folder when all your debug files are separated from other projects. So this is the first thing that I'm going to do here. Now for release only in advanced, I'm going to change copy content so that it would give me all the content file that I'm going to use. It would copy them to the output. And one very important is copy C++ runtime. Those two, the content and runtime, would allow you to have the ability to just upload the files as is, and it doesn't matter that your friends or the people that would download your project don't have the Visual C runtime redistributables, because the DLLs for those redistributables would be packaged in with your project. Now that we have those two changes, Visual C directories, to add the includes. I'm adding them from another project that I have already set up. Include directories, GLM library. So GLM is the OpenGL math library. It has a lot of structures that are very useful for OpenGL, and it also has functions for them, but most of the time I'm not using those functions. The SDL, this is the current version that I'm using. I didn't check if there's a newer one. Glue 2.2.0 is the current version. They haven't updated in a long while, but with all of those includes, we can continue. Now the library directories. Of course, the library directories are based on my library directories. I basically just, this is the x64 library directories, just those two. If I will add the GLM, there would be another folder for the GLM. Okay, apply, and then Win32. Same thing here. Library directories, edit. Okay, should be all of the things at the start. This is the project setup part. We need to change this. Coding language doesn't matter. I use C++ because I like coding in C++. The first file I'm going to make is going to be entry point. I call this file entry point because this file includes the main function, which is the entry point of the executable. It also includes a lot of other things that would be useful, and I'll have another file which is includes .hpp, which would have all of the includes for the projects. And this is weird, what's happened here. Oh, something wrong. Oh, yeah, because all of those are only on release. Apply. This should fix it. Okay. So let's start talking about this. First three includes glue, GLM, and STL. Those are very important for a few things. SDL is for having the ability to use the SDL code itself. GLM is to have access to the GLM types. And glue is, once again, for the extension wrangler to be accessible to us. If you're on Windows, including Windows.h is very useful. It solves a lot of stupid problems with Windows in general. Just for some reason, Windows decides to not include. You have it included here. SDL image for image processing, SDL TTF for true fonts, SDL mixer, if I remember correctly, SDL mixer is the sound. There are other things that we can add from SDL. There are a lot of SDL stuff, but just having access to those in general is very useful. Matrix transform is an amazingly useful function set. Basically just having an ability to transform, create a projection matrix and clip space matrix. All of those are very useful. And pointer type is just allowing you to get the pointer type for the raw data from the GLM structures. It's not very complicated. Those are just all useful things that we would use later. So, include all of the includes. I use HPP because first thing, it's making sure that you know that the header file that you're using is for C++. And okay, this. Okay, so all of our pragmas, this would make sure that everything is linked without inputting the exact linking file, the exact file you want to link into your properties. This is just manual linking instead of going into the project setup. We would have now a program that should run. Cannot open file sdl2 lib properties. Yeah, that's because okay, so I found the issue. I accidentally printed it in the winrt directories instead of the library directories itself. Apply. For win32, I actually printed the files on the correct line so it could compile. Now we run this, it would exit immediately, and from that point what I'm going to do is I'm going to go into the configuration manager, edit, and completely remove the x86 configuration, close. Yes, I don't want a 32-bit version of my game. What I'm going to do is I'm going to go into the project folder. I'm going to paste all of the relevant DLLs in that folder, selecting them all, content, true. It is going to make things messy in the folder. So another thing that we would do is we would make a new folder code, new folder content, and our entry points and include are going to be in code. This means that those should be removed. Add existing items, content, no, code, debug project setup, and when we are going to run this on release, I did it only for release to copy those because that's a deployment folder, and then project setup, instead of debug x64 release, you see that you have all of the DLLs included. So when you run this, it's not going to show any bugs. It's also not going to open anything because currently the code is just an empty main function. So let's start with doing something, making a new item, controller. I love to also make another class drawable and make controller part of drawable, just so controller also have access to stuff and would set up stuff that is useful for drawing. For the OpenGL context from SDL, we have SDL GL context. It's a void pointer, but it just has a type def to tell us this is going to be our GL context. It's a global, and we're going to declare it when we make our stuff in the controllers. Okay, so what is the controller going to have? Private members are going to be quit window. Later on we would have a level. For now we don't need to worry about level. We have an enum for all of the errors, so we can handle the errors. This can be set to 0, so we know exactly that if the controller is okay, then it's 0, and that would be the return value from the init. So we would have an init, get all of those, update and render function that we need. We would have a loop, and we would also have a function for cleanup. So let's start with init. Please fix this problem because it's a member of controller, and for now cont OK. Start up with initializing SDL. SDL init video, get the SDL log critical, category application, fail to initialize SDL, why? Get SDL error. Return cont SDL init. The controller couldn't init SDL, that's the return value, otherwise do this. Now we would set up the OpenGL parameters, attribute for OpenGL, major version, minor version, profile max is core. We're using OpenGL 4.3 core, pretty advanced, but is still compatible with most computers that are running today. Double buffering with zbuffer, OpenGL window. Just create window with a title, screen width, screen height, and should it be full screen, it's going to be an SDL window OpenGL with window shown. Here there would be the SDL issues when SDL can't make this. Quit condition failed on window error, and let's run this. Right, so what we're going to do now to add this is we're going to include controller. Now we're going to make a controller gcontrol controller.init. No idea what the screen resolutions should be. The old ones are 800 on 600. So let's do this test project, this thing and full screen set up as default values, and let's run this. It should create a window and close immediately. Back to the controller, we go into the OpenGL context, gcontext, which is from the drawable. Yes, because it's a static member, it needs to be declared. Another thing, gcontrol cleanup. What we're assuming in the case where the controller returns a failure is that we're going to return immediately, because if init fails, we are assuming that nothing has been allocated. And we can see that we are calling SDL destroy window and SDL quit when we added the gcontext failure. SDL GL set swap interval to -1, meaning that vsync is active. 1 for updates synchronized with vertical retrace. If the system supports it, you may specify -1 to allow late swaps to happen immediately instead of waiting for the next retrace. It's just about glue. It's SDL GL, delete context, gcontext. We put it before the destroy window. What we did is destroy window, then SDL quit. Now delete context, destroy window, and SDL quit. Glue doesn't really have any cleanup functions. We leave it at that. We can add the SDL subsystem mix, TTF, and image to the quit, and we can also set those back to null in case we somehow do controller cleanup and then reinitialize controller. Now starts with the loop. Loop-de-loop. Render would be an empty function, and update would be another empty function. So while we do not quit, did we set up the entry point to gcontrol loop? We have an SDL event while we call those event. If the event type is SDL quit, we set quit to true to stop this. This should open this window. Now we can see an empty window. We click close and it would close. Drawable should get its own header. This way we can include the drawable in other components without exposing them to controller directly. Another component which is part of controller would be a class which we would call level. It is a drawable, virtual render, virtual update, load, and unload. This class is just an interface. What would happen here is if current level, then current level render. and cleanup if current level unload. Now what we do is we add load new level, unload this, unload, then current level equal new level. Now this function called unload if current level. First we do current level unload, current level delete. We could also just get rid of those ifs by assuming that current level is always loaded. This is something that we are currently doing with safety. Current level equals null. We can extract level into its own thing to completely hide controller from people that use level. In entry point, g control dot load, and we should load our level. So just to make it possible, our level, it should include level and should have a class our level public level. Entry point include our level new our level. Load and unload are currently empty. Render is going to get some stuff in it, and update is currently going to have nothing. Yes, the only thing that works is GL clear with GL color buffer bit and GL depth buffer bit, and then GL clear color with a background color of some sort, and that is currently the only way around. But from this point we also need to add in the main loop for controller, we also should have current level input and current level, a current event. Then in our level we would add an implementation for that. Another thing that we would want to pass is quit here, and remove quit from here because it's not relevant. And now it should work when we press escape. This stops the function, and now we have input handling. Okay, so now that we have our level with some sort of input and an update function and some render function, let's start by adding all of the OpenGL handlers. We can call it just render pipeline. Let's add includes string because it's annoying to use stuff other than string, and all of these vertex attributes, a vertex attribute element to generate vertex arrays. Vertex arrays are elements that tells the shader what are the attributes they get. Setup buffer layout basically gives you this, you need the stride, an array of attributes which have the element type, amount of elements, and what is the amount of padding in bytes after that element, and then the number of those attributes. You can bind and unbind, and this is a vertex array object. Vertex buffer, this is what holds the actual data that is then referenced by the vertex array to extract the actual data for the shader. You can set up the buffer with data, elements, stride per element, and the usage type. Then you can update that data to basically take the setup buffer and give it a new data. Then you can bind and unbind it, save VBO, vertex buffer object, stride and usage, and element buffer, that's for indexing. Basically you have vertices in a buffer, and you have a vertex in 1,0, another vertex in 1,1, a third vertex in 0,1, and then a final vertex in 0,0. And you want to draw them in triangles. You can draw them as 3, 0, 2, then as a 0, 1, 2, and it would draw them as a rectangle. And this way you can actually set up the rotation type and all of those other things, and you can use the same vertices multiple times. Like here 0 and 2 are used twice. So this is what element buffer does. It is used by a few things. Then we have the shader base and the shader class. Okay, so let's go into make vertex array. Make vertex array is just generate the array and then bind. Bind is just this. Unbind is this. And then for this, what we do is we bind the vertex so we can set it up. Then we set the stride, and for each of those we have, for each attribute we enable the attribute. We would calculate the element size and the attribute size and the GL type, and for each of those we would have something different. Most common one, which is the default, is a float. Element size is size of float. Attribute size is element size times number of element. GL type is this. Then attributes, GL vertex attribute pointer, I attribute elements, GL type, false, all of this. We are going to use GL vertex attribute I pointer for integer types. Of course, this is the offset, and we started with offset 0, and we advanced the offset by the pad with the attribute size. So let me just add, without explaining too much, the rest of the attributes. Boolean, all of them have the same stuff. GL type is basically the type. Element size is the size of the element, and attribute size is this. Now, we can technically just remove this line from all of them and calculate it because it's the same line. So we just set the element size and the GL type, and Boolean is size of char. We can do size of bool, and we see that it takes 1 byte anyway. I do it like this because I know that a boolean is going to be a character size, so I set it like this. Int, same as uint in terms of size, float, and I could add more stuff, but that is enough for all of my use cases. If I want to add anything else, I can just add it here, but double, then case vat double, GL double, and we add vat double here. It is that simple. So now we have the vertex array setup, and we completed everything we need for the vertex array. For vertex buffer, we have to set up the buffer. So what we do is, first we generate the buffer, set the stride and usage, then we bind, and we update the data. Okay, so let's go with bind and unbind, which are very simple. Bind, just say bind VBO. Unbind, just say bind 0. Okay, and now for update data. It is a very complicated function. We first bind, so we can remove this bind from here. Stride times element data usage of the bound vertex array buffer. This data is the input data that we're going to use to update, with a buffer size of stride times elements, which is elements, and we know the stride of each element in the buffer because this is using the VAO, so it needs to be static, it cannot change. We have here the data, and we set the usage at the start, and the usage doesn't change. So now we set up the vertex buffer. We don't need the element buffer currently, but I will set it up anyway. Okay, so element array buffer, amount of elements and size of unsigned int, because every element in an element array buffer is an unsigned int always. And we have a data and have the usage of this element array. Okay, now for shader base. Okay, let's go with shader base constructor. Program ID set to 0. That's all we need for the program ID for the init. Same as everything else. GLUse program is program ID. Unuse is use program 0. And the others are just set uniforms. There are a lot of functions, basically uniform 1int, uniform 1f, 2f, but instead of passing it as two floats, we pass it as a glm vec2, set float 3, but with a vec3 from glm, set matrix, get gl uniform location, program ID C, 1 transpose glm value ptr, gl uniform matrix for fv. We can add other stuff. I'm not going to get into this. This is annoyingly complicated to explain in a simple manner, but it's just there for passing the transformation matrices for rendering in 3D. We need those later on as uniforms. And we are using std string here instead of char constants, just because it's easier. And we're passing them as const references. For our shader, we just do this to allocate everything as 0 and false, and another empty. So now we have the pre-make. We're going to use string streams and file streams. So we need to include those 3 headers, which are fstream, sstream, and iostream. Just to explain, we set up shader code string, shader file ifstream, input file stream, and then shader file exception, fail bit, and bad bit. Try to open file and catch it with an error message so we can actually know shader file didn't read properly. And here we have a shader type and a shader path that we get. Then we use the CSTR for the shader raw code, and then we pre-make string. After this pre-make string, then the program exits and the string itself deallocates. So even if we only pass this, it still is relevant inside pre-make string. It doesn't get deallocated, so it's fine. So now let's start with pre-make string. For pre-make string, we have shader source, the name of the shader, and the shader type. Here we only had shader path and shader type. Shader path become the shader name, and shader type stays the shader type. The raw shader code is in here. We have our integer success. This would be tested for if we fail or succeed. Info log. This is the string that we're going to write into. It's a character array. This is a const char pointer for our type string, for our static string types, and shader type GL for the district type. This is, after all, our personal enum, so we need the GL type of the enum. So we are only able to support those 3 types of shader, the vertex shader, geometry shader, and fragment shader. If we want to support more types of shaders, we would need to add implementations for them. So currently, those 3 are the only ones supported, and if we have something that isn't supported, we have this, and we return because we failed. And then what we do is we have the shader temporary handle. We create a shader, we add the shader source, we compile the shader. If there are shader errors, we output them, get shader info log, here shader temp and info log, 512 bytes into info log to tell us what kind of error we got. And if we got that error, we return. Otherwise, we set the component with that type, either vertex, geometry, or fragment shader. We set it to true, and we tell that the temporary shader that we made is actually compiled. Then when we link, we go over all of the supported shaders, and we test if the component link is true, if we need to link the component, and then we do the GL attach. We link the program. We get link status. If we have any error, we say linking failed with the error, and then we clean up all of the shader components. And then we also can add a deallocator if first of all, this false and this program ID, gl delete program ID. This is the cleanup. Now we need to remember to add the constructors for all of those. And EBO. Now this also does cleanup properly for all of them. And with a shader program, new item, we can go here into content, new folder, shader. We're going to use a text file. We call it shader1 avert. Let's do this. I won't explain the shaders currently because genuinely it doesn't matter. Those shaders would only matter later. Shader1 flag. And now our level render pipeline, shader path, content, shaders, shader1 verts, shader vertex, geometry, and flag, shader link. Great. Run it to see that all of the things compiled properly. Yes, a VAO and a VBO, 800 and 600. Later on, when we want to make stuff globally accessible, we can add another include and call it properties, which would include the screen width, screen height, and all of the stuff that we might want to do. Now let's just generate this, and for points, have points, vertex amount, and let's see, is everything working okay? No, because the width is 800 and this is 600. Yes. Now we go into rendering, and after that we add this, and as we can see now it does draw the vertices, so we can render things onto the screen. We can get input. Let's add another one, which is that we do VBO and VBO dot update data points vert amount. Great. Break case SPL mouse motion break points 0 equal to C event dot motion x1 is y, and now so y would be 600 minus y, and now it fits with mouse position, and we update it every time. As the first element, it passes behind the two other, and we can also add other things. Case SDL mouse button down is equal to SDL M, maybe? No, SDL mouse. Let's enter here, mouse button index. There should be an enum for this, but let's see. If it's 0, then points 2. So now when I click, okay, let's check what is button. Button is 3. Right click is 3. So this is 1 and this is 3. Okay, let's reset. Now we can handle changing all of the vertices based on input. So now that we have mouse motion, mouse button, key down through SDL, we have pretty much anything that we want to do. Those shaders that I did are just used to generate a texture, a generic texture from an input of an integer vector 2. It creates the size and the sprite index. If we remove the geometry shader, we can still use GL point size to generate points that are not microscopic.